Hello everyone, I'm Zeng Cheng. We'll study the last part of this course together. In our course, lots of mathematics will be involved. However, math is just the same as words. It's a tool to express ideas. Therefore, in our course, I'll try as much as possible to show the ideas expressed by the mathematics to you. Hi, we'll discuss the simplification of the signal flow graph in this lesson. We learned from the last lesson that a signal flow graph is a graphical representation of the system function. The simplification of a known signal flow graph is to get the signal function represented by this graph. In this section, we'll briefly discuss the general way of signal flow graph simplification first, then a formula to simplify the signal flow graph directly, which is the Mason formula, will be introduced. Now, let's look at the ordinary way to simplify a signal flow graph. There are a few rules in signal flow graph simplification. The first one is the merging of cascade branches. The gains of cascade branches are multiplied. For example, the equivalent branch gain of the cascade branches A and B is the product of A and B. The next rule is the combination of parallel branches, in which their gains are summed. For example, the equivalent branch gain of the parallel branches A and B is A plus B. The last rule is the elimination of loops. This is the most important step in the signal flow graph simplification. For example, we have a signal flow graph like this. It has a loop. The most difficult task to simplify it is to eliminate the loop. So how can we eliminate the loop? We can list the equations for node variables in signal flow graph according to their input branches. Then the loop can be simplified as a self-loop. In this simplification operation, it seems that the branch B is split into two branches. One cascades with the branch A to form an equivalent branch AB. The other cascade with branch C to form the self-loop BC. After this, we can further simplify the self-loop to get the final result, in which the self-loop is actually equivalent to the branch 1 over 1 minus BC. To sum up, the basic steps for the simplification of signal flow graph can be listed like this. First of all, we should try to eliminate all the loops. Then, the cascade branches can be merged to reduce the number of nodes, and the parallel branches can be combined to reduce the branches. After simplification, a signal flow graph with only one branch is obtained finally. For example, this is a signal flow graph. Now let's try to simplify it with the steps introduced above. The first step is to simplify the two loops in the signal flow graph to self-loops, which is to take these two branches with the gain s-1 and split them. The one serves as branches in the forward path, the other forms branches in the self-loops. Once these two loops are converted into self-loops, the signal flow graph can be simplified further by combining cascade and parallel branches to this equivalent form. In this form, a self-loop still exists. We can simplify it with the method above to get the final result. In fact, the simplification is simply to convert a complex signal flow graph into the one with only an input node, an output node, and a branch, whose gain is the system function of this signal flow graph. This is the system function after simplification. Of course, the system function can be expressed as positive or negative power of s. This is the differential equation corresponding to the system function. In fact, the signal flow graph given by this example is a type of standard structure of signal flow graph. For the signal flow graph with this standard structure, we can directly write its system function based on some rules without any simplification. How can we do it? The first step is to determine the order of the system according to the number of integrators in the system flow graph. For example, there are two integrators with s-1 in this graph. Hence, it is a second-order system. For a second-order system, its numerator polynomial should have three coefficients. b2, b1, and b0. Similarly, its denominator polynomial also has three coefficients. The first one is usually normalized to 1, and the other two coefficients are the minuses of the gains of these two inverse branches. Therefore, we can directly write such a system function whose numerator and denominator polynomials depend on these coefficients. Next, let's look at another way to simplify any type of signal flow graph directly, which is the Mason formula. The Mason formula is made simply of the denominator and numerator. The denominator delta, we call it the characteristic determinant of signal flow graph, is formed by the following items. 1 minus the sum of gains of all loops plus the sum of the products of the gains of every group with two non-touching loops, and then minus the sum of the products of the gains of each group with three non-touching loops. If there are more loop groups with 4 or above 4 non-touching loops, it should continue to plus that of loop groups with 4 non-touching loops, and minus that with 5 loops, and so on, until no more non-touching loop groups can be found. The numerator is composed of the sum of several terms. The ith term, pi, refers to the gain of the ith forward path from the source node to the sink node. The delta I, derived from the characteristic determinant delta, is called the cofactor for ith forward path. It's obtained by removing all the loops which are in touch with the ith forward path, setting loop gain to 0 from the characteristic determinant. So it's named as the cofactor of characteristic determinant for ith forward path. Now let's simplify the signal flow graph, which we simplified in an ordinary way above with the Mason formula. There are two loops in this signal flow graph. The loop gains of them are minus a1, s minus 1, and minus a0, s minus 2, respectively. It doesn't have any non-touching loop, hence both of its loops are in touch. Therefore, its characteristic determinant is 1 minus the sum of all loop gains. As to the forward path, there are three forward paths in this signal flow graph, such as these three. The gains of these three forward paths are P1, P2, and P3, respectively. Since all the three forward paths and the two loops in this graph traverse through node x1, all the loops and all the forward paths are in touch. So we don't have any loop which doesn't touch any forward path. So all the cofactors of the three forward paths are 1. Finally, we can get the system function of this system. The denominator is the characteristic determinant, while the numerator is the sum of the product of the gain and the cofactor of the forward path. The cofactor for every forward path is 1, hence the numerator is actually the sum of the gains of these three forward paths. This is another example. There are 4 loops in this signal flow graph. This is the first one and its loop gain. This is the second one and its loop gain. There's the third one and its loop gain, and the last loop consists of several branches. This is its loop gain. In these 4 loops, there are 2 non-touching loops, which are these 2 loops. The product of their gains equals to G1, H1, G3, H3. We can't find other loop groups with 2 or above 2 non-touching loops anymore. Therefore, the characteristic determinant of this signal flow graph is 1 minus the sum of all the loop gains and then plus the product of the gains of the 2 non-touching loops. Because there's only a pair of such loops, we don't need to sum products. As a result, we get this characteristic determinant. Now, let's go to the forward path. There are 2 forward paths in this graph. One is from x, x1, and x4 to y. The other is this one. The first forward path does not touch this loop, while the second forward path touches every loop. Therefore, the cofactor of the forward path P1 is 1 minus the gain of this loop, and the cofactor of P2 is 1. Now we can obtain the system function of this system based on the above results and Mason formula. Its denominator is the characteristic determinant and the numerator is P1 delta 1 plus P2 delta 2. Finally, let's make a brief summary of this lesson. Firstly, the system function of a signal flow graph can be obtained by simplification. Secondly, the basic steps to simplify a signal flow graph are eliminating loops at first, converting them to self-loops, then merging the parallel branches and cascade branches. Thirdly, with the Mason formula, we can directly write down the system function of a signal flow graph without any simplification. However, it uses some concepts related to loops and forward path. And that is the end of this lesson. Bye.